Okay. Hello, everyone. Let's get this recitation started. So I guess some of you have, I guess you've seen me in videos. Okay. I want to say you haven't seen me really. I won't say in person, but you clearly haven't seen me in person. I guess you haven't seen me in a live virtual setting or something like that. So I will be teaching instead of Professor Phillips today. She made the announcement last week about this. She's giving a talk at a conference, and so she couldn't teach today. And in today's presentations, we'll cover combinatorics, which is what the last couple of lectures were about. Okay, so let's get started. You can ask questions whenever you want. Either ask them in the chat, or even better, just speak up, unmute yourself, and ask the question. That works great as well. So before we dive into solving a couple of problems on combinatorics, I have a bunch of announcements I want to make. So first of all, quiz 3 was last week. We're almost done grading it. We will hopefully post the grades later tonight, and if not, then tomorrow the latest. Another thing I wanted to mention about quiz 3 is that TAs brought up concerns about the length of quiz 3 to our attention. Some students mentioned it during the discussions last week. And so we'll discuss this. Quizzes 4 and 5 are usually on the easier side anyways, but we'll take this feedback into account as well when creating them. So thanks for bringing this up to our attention. Then another thing I want to mention is that we'll try to grade homework 4 by the end of this week. The deadline was on Friday. And, because both of them were kind of due around the same time, it's hard to grade everything quickly, but we'll try to do it by the end of this week. And we released homework 5, which is on counting. So take a look at it, start working on it, don't delay it. Finally, one more thing. So next week is going to be a little bit different because, as you all probably know, the elections are coming up. So the elections will be on Tuesday next week, November 3rd. And we already announced this, but I'll stress it out again. As per college guidelines, there will be no synchronous recitations that Tuesday. So that Tuesday, you should not be tuning in for these Zoom meetings and so on. Instead of that, we will post recorded recitations to YouTube, and we'll make an announcement on that, about that. So you can watch them whenever you want. On top of this, again, as per college guidelines, there will be no office hours on Tuesday and Wednesday next week. So we didn't want to force TAs to do office hours because they want to vote as well. Instead, the only office hours that we will have are my office hours on Wednesday morning from 9 to 11. So if there are homework problems or some of that you want to discuss, come to my office hours on Wednesday. Or if you just want to discuss the results of the election, come to my office hours. And finally, we're doing all of this so that you guys can go and vote. So I strongly encourage you to do that. If you haven't registered so far, you can still register in person and easily vote. So take advantage of that opportunity and just do it. So these are my announcements. Any questions about any of these? Okay. So before we get to the problems, I just want to quickly review what we covered in the lectures and some basic rules for counting and so on that we'll be applying to solve the problems. So we introduced a couple of different rules, rule of products, rule of sums with overlaps, and rule of complements. And we'll be using 3 out of 4 of these in the upcoming problems. So I won't revisit them here again. And then on top of that, we introduced 4 different structures that we apply in counting. So those are ordered lists with repetition, permutations, combinations, and unordered list with repetition, or bag. And then, so how do we decide which structure we have to use? Well, if you remember in the lectures, we had that table where x-axis was, or columns were related to whether we have repetitions or not, and rows were related to whether the order matters or not. So first, you have to therefore figure out the answers to these 2 questions, and then based on that, you choose the structure you have to use. And we also derived expressions or formulas for how to count objects belonging to these structures. And I'm listing them here again. And again, I'm not going to go through these. So you should know all of this. And you should know all of this in the quiz as well. Okay. So I think I have 6 problems, but I will not have time to go through all of them because I give you time to solve them on your own. And we'll also do at least one breakout room session where I'll split you into Zoom breakout rooms and you'll be able to discuss the problems and so on. And so I cover different problems in different recitations today. So for problems that we do not manage to cover in this recitation, you're more than welcome to watch the videos of other recitations and see the solutions there. Okay, so this is the problem we'll start with. So Charlie and her girlfriend Amber go to lunch at the restaurant that serves 8 sandwiches on the menu and 3 beverages on the menu. They order 1 sandwich and 1 drink each, and you have to calculate in how many different ways can they make their order. If they must order a different sandwich, but they can order the same drink. An important piece of information here is also that we don't care which one of them orders first. So that tells you that the order does not matter for this problem. Okay, so I'll give you a couple of minutes to try to solve this, and then I'll solve it for you. The total count for this problem is not that high. And so I will also ask you to calculate the final number. On the quiz, we will specifically note whether we are looking for the final number or not. And if the number is small, we'll ask you to calculate. If it's really large, you can kind of leave the final expression in the solution. Okay, so yeah, give it a try. The way I went about this is that I calculated the different ways we can order sandwiches, and then the different ways we can order drinks, and then I kind of combined those to get the final number. Okay, so give it a try. I'll give you maybe 3 minutes, and then I'll solve it for you guys, and then we'll answer any questions you might have. And by the way, if you're done calculating this, I encourage you to write in the chat what is your final count. I'm just curious what people calculated. Okay, still no correct count. It's funny. Some of you undercounted, some of you overcounted. Okay, so let me do this for you. Thanks for everyone who kind of shared their count. Okay, so let's do this. Okay. So like I said, I'm going to count the number of ways we can choose sandwiches first, and then drinks. And then I'm going to use rule of products to get the total number of different orders. So sandwiches, they cannot order the same sandwich. So that means that there are no repetitions. And as I already said, the order does not matter. So no repetitions, the order doesn't matter. So these are our combinations. So we are choosing 2 sandwiches out of 8 possible different sandwiches. So that is equal to, we can calculate it out, 8 factorial divided by 2 factorial times 6 factorial. So these cancel out and you are left with 8 times 7 here. So that is equal to 8 times 7 divided by 2 factorial. That is equal to 28. So there are 28 different ways that they can choose sandwiches. Now we have to calculate drinks. And let me finish this and then I'll respond to questions. So there are kind of two different ways that you can do drinks. This time around, I will apply the rule for bags, because selecting a drink is like filling up a bag of size 2 and choosing from 3 different items, because the order does not matter, but we do allow repetitions. So then for drinks, we have choose, if you remember the formula, it's n plus r minus 1 comma r, where n is the number of items, which is 3 in our case, and 2 is the size of the bag, which is 2. So that's equal to choose 4 comma 2, and that is equal to 4 factorial divided by 2 factorial times 2 factorial, and that is equal to 6. And so the final count is 28 times 6, which is equal to, what do we have, 168. Okay. So, any questions? Good job, Parker. You fixed your mistake and got the correct answer. Any questions?
So someone asks, how do we differentiate when order does or doesn't matter?
Good question. So the question or the problem will tell you whether the order matters or not. So it will always give you a hint if the order matters or not. If you're unsure on the quiz, feel free to ask us on Piazza. And we might or might not help you, depending on, whether the question gives you a hint about the order or not. So here, this last part tells you. So the last part says, regardless of which one orders first. So that means, if you think about it, that, if Charlie orders sandwich 1 first, if Charlie orders sandwich 1 and Amber orders sandwich 2, or Charlie orders sandwich 2 and Amber orders sandwich 1, these two are equivalent. The order does not matter. So the question will always give you a hint whether order matters or not and whether there are repetitions or no. Any other questions?
Yeah, I have a question. So wouldn't, in this case, wouldn't it mean though, since Charlie got a different sandwich than in the first case, it is a different combination?
Sorry, could you repeat the question, please?
Yeah, that because in the first case where Charlie chooses sandwich 1 and Amber chooses sandwich 2, and then in the other equivalent case, Charlie gets sandwich 2. In my head, I see that as a different combination just because Charlie got a different sandwich in the end, so therefore it's a different combination. But yeah.
Yeah. So that's a good question. Let me think about this. Great question. Okay, let me try to explain this. I like this question a lot. So I wrote something like 1, 2, 2, 1. Yeah, I actually explained this in a wrong way. So what is equivalent is the order where Charlie orders. I should write this differently. So we have the order. We have the case where Charlie orders first and orders 1, and Amber orders second and orders 2. And that is equivalent to the case where Amber orders first and orders 2, and Charlie orders second and orders 1.
Okay. Yeah, that makes a lot more sense.
Yeah. So this is what I was trying to say, and I said it in the wrong way. So thanks for bringing this up. Great point. Any other questions? Okay, so let's do our next problem. Let me choose. This is exactly the one I wanted. So our second problem says you're playing a lottery where tickets have 7 ordered boxes, and each box can be any of 3 colors: red, green, and blue. And two example tickets are RRR, GB, GB, and RRR, GG, BB. And those two tickets are distinct tickets. So I won't provide you hints anymore about order and repetitions and so on. You should figure it out on your own. So there are two questions here. How many possible tickets are there? And question B, how many possible tickets have at least two R's, two G's, and two B's? The first one should be pretty easy, straightforward. The second one is kind of similar to those problems that we had in the lectures with like letters. I think it was like Mississippi and how many words can you create and so on. So you can solve it using the same strategy. And so I will split you into breakout rooms for this. However, I cannot share the slides with you in the breakout rooms. So maybe I'll give you like 30 seconds and you can note down, the basic things. 7 order boxes, choosing between RGB, and then A is how many possible tickets, and B is how many tickets have at least 2 R's, 2 G's, and 2 B's. I've actually copied the whole thing in the chat as well, and you'll be able to see it there. And then we'll do breakout rooms. Yes, screenshots work as well. Okay, you have it now in the chat. Let's do breakout rooms. You'll have to click join the breakout room once I start it. Feel free to discuss it, of course. Feel free to solve it together. Have fun. Oh, and James, if you could join one of the rooms as well to kind of help out these students, that would be great as well. Thank you. Okay, welcome back, everyone. So I hope this was nice and fun. So let's do these. Okay, so what do we see from the problem? The order matters and repetitions are allowed. So part A, this is our ordered list. And that's going to be, we're choosing from 3 colors. And there's 7 of them, 3 to the power of 7. Okay. Part B, it's a bit more involved. So let's analyze it a little bit. So how many possible tickets have at least 2 R's, at least 2 G's, and at least 2 B's? The total number of boxes is 7. So if you think about it, there are only 3 ways that this can happen, that this can be satisfied. And that is if we have 3 R's, 2 G's, 2 B's, or 2 R's, 3 G's, 2 B's, or 2 R's, 2 G's, 3 B's. So these are the 3 different ways that this B can be, part B can be satisfied. And so each solution or each configuration that is solution to part B belongs either to the first row here, or to the second, or to the third. So because we have or between them and they are mutually exclusive, we can calculate each row and add the count up. So how do we calculate the first row here? So we do this using the strategy, like I said, that we used in that Mississippi problem in the lectures. So we imagine that we have 7 of these boxes. 1, 2, 3, 4, 5, 6, 7. And the algorithm goes as follows. First, we choose 3 slots to place these 3 R's out of 7 slots total. So that's going to be choose 3 out of 7 times. Then we choose 2 slots out of 4 leftover slots to place the G's. So we are going to choose 4 out of 2 to place the G's. And then finally, we are going to choose 2 out of 2 to place B's. And when you calculate this out, well, okay, let's finish it. So that's the first row. The second row, we have plus. Plus is almost identical. We are choosing 2 out of 7 times choose 3 out of 5 times choose 2 out of 2 plus third row, we are choosing 2 out of 7 for R's times we are choosing 2 out of 5 for G's, and then we have 3 B's with 3 leftover slots, and that's it. And so when you calculate this out, you get your final solution, which should be 630. So that's how you calculate part B. There are other different ways of doing it. I would say this is probably, for me, at least, I think this most straightforward and the shortest one. Okay, any questions at this point? Okay, no questions. Great. So this same example.
I have a
Go ahead.
question.
Yeah.
So the way that I set up this problem was I selected the 7 boxes, and then I did choose 2 out of 7 times for the reds, times choose 2 out of 5 for the greens, times choose 2 out of 3 for the blues. Is that also a legitimate setup for the problem? Because I got 630, which was the right answer.
So you choose 2 out of 7 for reds, then 2 out of 5 for
the greens, and then 2 out of 3 for the blues. So instead of setting it up where it's the 3 individual ones,
And did you then multiply that by 3?
Well, that's the choose 2 out of. Yeah, so Parker has it in the chat. But there's, well, I mean that's what I did, and I got 630.
I have to think about this. So there's another question. So you placed, 2 reds, 2 greens, 2 red, 2 green, and 2 blue, and you chose their spots. But you still had to fill up the 7th spot. And so you have to choose which of these 3 you are going to put in this leftover spot. So, so what is strange to me is why you don't have to. Are you then over counting? I have to take this on offline. Sorry, this is, but I will post it on Canvas.
Okay.
I mean, I like seeing different solutions, and right now I don't see a problem. I mean, I see a problem with yours, and so I'm surprised that it ends up being 630. So let me think about this, and I'll post it on Canvas. Great question. So Elizabeth asks C73, C72, C5. Yes. So the answer to Elizabeth's question is all of these 3 rows will be the same number. So in fact, you could have calculated one of them and just multiplied by 3. So there's a question by Dan in part B. Why do we use C and R instead of C, R plus N minus 1 minus R? So why are we not using bags? So because we are not allowed to repeat spots, right? So this C73 means we are choosing 3 spots out of the 7 for red red outcome, and we cannot repeat them. We cannot put 3 reds in spot 1. So that's why. Yeah, so Tori's solution, so it's choose 7, 3 times 4, 2 times choose 2, 2 times 3. That's a good solution. Okay. Any other questions? Okay. So let's move on and try to do one more problem. And I have a particular one I want to try. Yeah. So here is the one I would like to try. So a briefcase has an ordered 3-digit lock. And then we want to calculate 4 different things. How many total configurations are there? How many configurations there are if there are no repeated digits? You can use any of the 10 digits, right? From 0 to 9. How many configurations have 8 appear exactly twice? And how many configurations use the digit 0 at least once? I'll give you a couple of minutes to try to solve this. A note about the last one. There is a pretty simple way of solve it if you use one of the rules we haven't used so far. Let me say it like that. So please give this a try. Okay, so let's go through all of these one by one. So how many total log configurations are there? We're allowing repetitions. The order matters. There is 10 digits, 3-digit log. So it will be 10 to the power of 3. So that's our order list. Okay. How many configurations have no repeated digits? So these are our permutations. So it's P, P of 10,3, and that is equal to, actually, in the interest of time, let me just leave it like this. It's okay. So P of 10,3 because we are not allowing digits to be repeated, but the order matters. How many configurations have the digit 8 appearing exactly twice? Okay, so it's exactly twice. So it's a little bit related to the previous problem we solved. So we can first choose the two spots in which we are going to put 8. So we are choosing 2 spots out of 3, and we're going to place 8 in these 2 spots. And then for the leftover spot, we have 9 possibilities because we cannot put 8 there. And so that's the solution to this one. So it's equal to, this is a little bit easier to calculate, 3 factorial divided by 2 factorial times 9, 27. Any questions about this one, the part 3? Okay. Part 4. How many configurations use the digit 0 at least once? So the way I went about this, and I think it's maybe the most straightforward way to calculate this, is using the rule of complement. So we can calculate this number by calculating the total number and subtracting for it the opposite of use digit 0 at least once. So the opposite of this is minus do not have 0. So this will give me the answer to this problem. So using 0 at least once, the opposite of that is having no 0 at all, no zeros at all. And this is pretty easy to calculate. So the total number we already did in part 1. So that's 10 to the power of 3 minus the total number of configurations that don't have a 0. So we just remove the digit 0, and then we have 9 digits and 3 spots. So that's the solution for this one. When you calculate this out, what do you get? Let me see. I have it here. Well, okay, I don't have it handy. 1,000 minus, okay, my old brain. 81 times 9, 9 times 8, 72. And that is equal to 271, if I didn't mess it up. Okay. Any questions about this one? Hey, there is another 271. Thank you, Parker. My old brain still works, kind of, I guess. Any questions? We're almost done. Thank you. Thank you. Okay, any questions? Going once, twice, third time? Okay, then we'll wrap it up here. Make sure to check out other recitations because I solved a slightly different set of problems. And thank you all for joining. This was fun.